Engineering Dynamics, Session 1, a Kinematics of a Particle. In general, engineering mechanics divided in three main branches of rigid body mechanics, deformable body mechanics, and fluid mechanics. Mhm. And the first group, it just goes to two branches of statics and dynamics, which is the course of our semester, and that's a very interesting journey through a very early work of Leonardo da Vinci, or father of dynamic, which is a Galileo Galilei, and to the Henry Ford, Newtons, and the other influencer in dynamic knowledge. And statics works with the rigid body when they are at rest. So in this figure, you can see a graph of an aeroplane, which is the forces are in balance. The vertical forces are in balance, so it's at rest. Or uh, the dynamics talks about the rigid bodies when they are in motion. Mhm. That's a concept of equilibrium. That's a balanced condition. And in a general approach, a mechanics is divided into classical mechanics, quantum mechanics, relative mechanics, and just forget about the two rest. Just in classical, in a rigid body, not all of them, just we are considering the dynamic for our course. Mhm. So definitely we do have deformable bodies, which goes to strength of materials, and uh, elasticity and plasticity theory, fluid mechanics, thermal, heat transfer, and gas dynamics. I already covered this course in a free online a YouTube in the same channel. You can uh, visit it, and there are plenty of interesting example in terms of strength of materials out there. Mhm. Galileo Galilei, called the father of dynamics in 15th century, and that's a born in Pisa in 1564, and is a Italian scientist. These are the very early work of Leonardo da Vinci in even 15th century. Mhm. And you can see a train moving a something like a sand buckets, and it's these are the early drawing of a genius called Leonardo da Vinci in 15th century. And you can see later on how Galileo Galilei, the father of dynamics, look at the great work of the past, and that's a something like a century later in 16th century. Leonardo da Vinci, born in Pisa and live in Arcetri, located in Florence, Italy, in Tuscany, among the hills of South. And that's a photo of the living room of Galileo Galilei in 16th century. So that was a brief introduction to the history of a two influencer in dynamics knowledge. So there are plenty, many more of them. So let's go to quantities, dimensions, and units. So we have a quantities like mass, length, time, force. These are our four dimensions. And dimension of them are m, l, t, f, all in capital. Unit divided into two units of SI, and the other one is US customary unit. So in the SI, that's a kilogram, meter, second, Newton, and the symbol stand for kg, ms, and capital N for Newton. And in likewise in US customary, that's mass goes by slug, foot, seconds, mass is go by pound, and that's feet, second, pound. Mhm. That's interesting. This is the US standard kilogram at the National Bureau of Standards. So if you magnify this small piece over here, that's the same standard kilogram, which is the base for measurement in the US Bureau of Standards. Mhm. Again, for unit, we do have a 1 Newton is 1 kg times 1 meter over square square seconds. Likewise, a 1 pound force is a 1 slug, a mass over acceleration, 1 feet over square seconds. Mhm. That's how we define them. So if we want to just consider what we'll study in dynamics, that's a path of rectilinear translation. We can have a translation in a straight line, like in time t and time t prime, the object moves in a straight line condition. Or it can be a path of curvilinear paths of translation or travel, which in the t prime, it just climbs a bit down as it comes down the road. Mhm. And you can have a rotation about a fixed axis. Mhm. We have different scenario which we will cover in the term of discourse. Mhm. And we can have a general plane motion which consists of curvilinear plus rotation. As you can see in the second figure is also translate to the new location and also rotated or tilted in a different a condition or configuration. That's a general. So motion in dynamic goes to two main categories of kinematics and kinetics, which will study the kinetics and kinematics of a particle, then for a rigid body of them, which is a combination of particles. So kinematics is the knowledge which does not take into account the forces. So kinematics doesn't study the effects of the motion. Just kinematics is solely focused on study of motion, so only motion, and does not take into account any forces. Mhm. In the other hand, kinetics is the study of the motion and the forces that underlies those motion. So that's the cause and effect of motion as well. Mhm. So in part one, kinematics of a particle in engineering mechanics, mhm, we do consider displacement, that's S, velocity, acceleration, mhm, stands A stands for acceleration, B velocity, S displacement, and time, which is the travel, a time period. Any equation, any kind of equation which can any kind of relation between these four variables is called a kinematic equation. Mhm. First of all, erect linear motion, the simplest one. So at the origin you stand here, in time t you are here. This is origin. At the time t you have a distance from the origin, and at a t plus delta t time you travel a bit farther from the origin, and that's s plus delta s. That's a When you move in a straight line, that's a rectilinear motion. Mhm. So rectilinear is it's come from rectus plus linea. That's a Greek origin of right angle. That's a rectus in opposite of curvilinear. When you move in a something like a curve, that's a curvilinear motion. When you move in a straight line, that's a rectilinear motion. And we are interested to know what the velocity and speed and displacement are in terms of vector and the speed. So a speed is a scalar a value and velocity is a vector either in 2D or 3D. So displacement, the displacement of a particle is defined as a change in its position. That's a change in position. It's a displacement. Mhm. So what velocity is? We do have instantaneous velocity. That's a small derivation of a displacement over a small period of time. That's instantaneous velocity. And in likewise, we can have average velocity, which is a more extended of the distance over more amount of time. That's the average one. Hmm? The same, likewise, we can have instantaneous acceleration, a small derivation of velocity over time, that's acceleration. And at the same time, we can have average of that. That's a more extended, over a more extended of time, of velocity over a more extended of time. And if you want to know the geometric interpretation of instant velocity and acceleration, that's a that's v is ds over dt. Mhm. If you have a curve, your tangent at a very moment, that's a instantaneous velocity. If that's s versus t, displacements versus time, and that's a instantaneous acceleration if that's velocity versus time. So this is your curve, this is your tangent, and at the very moment that's instantaneous. If that's average velocity or acceleration. So in instantaneous velocity, we have a limit when t goes to 0, tends to 0. In average acceleration, we do have a more extended of time. Mhm. In likewise in instantaneous acceleration, we have a limit of delta v over delta t when delta t tends toward the runs to 0. Mhm. A differential equation. Let's define a differential equation for a kinematics of particle. Do you remember I told you any equation can relate S, T, V, and A together? That's a kind of a kinematic equation. So velocity is change of a displacement over time, and you can show it by also S dot because that's a derivation. Acceleration, likewise, is a derivation of velocity over time, and you can show it with V dot or S double dot. Mhm. If we call the first one equation 1 and the second one equation 2, and we write them based off only dt, dt from equation 1 is ds over v, and dt from equation 2 is dv over a. So both of them are dt, they are equal to each other. So that says ds over velocity, change of displacement over velocity, is exactly equal to change of velocity over acceleration. And that's very interesting because that gives us an independence from time equation. So that's one can say v dv, velocity times change of velocity, is acceleration times change in displacement. And you can show it definitely with a derivative format. That's s dot, which is velocity, times ds dot, that's a variation of velocity, that's equal to s double dot times ds, which is a times ds. That's a very useful equation. We'll talk about more a derivation and equation in session 2. Thank you.